to the American Physical Society, the Material Research Society, and so on. But I think Nader is most of all a friend, and we know that he loves Italy, so we are really, really happy to have him here. And today he will show us, he will give a great talk, I'm sure, on structuring light with extreme metamaterials. Thank you, Nader, for being with us, and thank you for delivering your talk. Thank you very much.
Thank you very much, Onofrio and Antonella, and all the friends and colleagues from University of Messina for giving me this chance to be with you today. It's a pleasure and honor for me to be here. And yes, I love Italy, you know, and I have many friends in Italy, and whenever there's a chance, I would love to come and visit you, as many of my friends know that I love to be there. And thank you so much for giving me this chance to be there, even though we are virtual Zoom. But hopefully this pandemic will be over and we'll get together in person. And of course, as Onofrio mentioned, we are very close friends, you know, we are collaborators, you know, Onofrio, Pino, Rosalba, Maria Grazia, and many friends, and our group, you know, working together on very exciting problems. So thank you so much for giving me a chance to be here. So let me share my screen right now. Now, let me, okay. 1 second. Okay. Do you see my screen now?
Yes, fine.
Yes.
Yeah.
Okay, let me put it on slideshow. Okay, very good. So when Onofrio and Antonella asked me to give this talk, I wanted to give an overview of 2 topics today. In general, in my group, we are very interested in physics and engineering of waves, and how we can actually manipulate waves. And in this case, I talk about electromagnetic and optical waves, using materials in order to do interesting things with the waves. And the metamaterial, of course, is one tool, you know, to manipulate and control light in order to do functional properties of the structure. So today I'd like to talk about 2 scenarios. And these 2 scenarios, actually, they are separate from each other, but somehow connected to each other as well. Now, but before I do that, let me just give a very, very quick, maybe 3 slides of what metamaterials are, and then we get into the main topics of the discussion today. So what is metamaterial? Now, we know that light-matter interaction is governed by the laws of electrodynamics, both classical electrodynamics, Maxwell's equation, and so on, and quantum electrodynamics. But usually when we like to actually study light-matter interaction, we would like to parameterize this interaction in the form of several macroscopic parameters that you're all familiar with. I mean, permittivity, permeability, conductivity, nonlinear susceptibilities, you know, chirality, and so on. By the way, do you see my cursor when I move stuff there? Is it clear? Okay, good. So now these parameters have certain ranges of values for the natural materials that we get, you know, from periodic tables, and the derivatives and combination of elements from periodic tables. But the concept of metamaterial, which has a long history, by the way, used to be called in artificial dielectrics in 1950s, and after that, it was called complex materials. In the last 20 years, it's called metamaterials. And the concept is that if you start with the host medium that you see, let me actually use my laser pointer so we can see that. If you see the host medium and then you embed them with man-made inclusions, these elements, man-made inclusions, when you have electromagnetic wave propagating through this, this wave is going to induce electric and or magnetic dipole moment on these inclusions. And as a result, when an observer sitting outside looking at this structure collectively, and an ensemble, you would say an effective parameters for this. Effective permittivity, effective permeability, and effective index of refraction. And in fact, these parameters may be quite different from the permittivity, permeability, and index of each individual elements of this over here. One of the interesting points, by the way, about the this concept is that you have several degrees of freedom that you can control in your design. Composition of these inclusions, alignment and arrangement on these inclusions. In other words, what are these made of? How are you distributing them? Whether you distribute them randomly or you distribute them, you know, in a periodic fashion. Density of them, how many of them per unit volume you put there, host medium. And last but not least, the geometry and shape of these inclusions. And particularly this last item have become a very interesting point in the past 2 decades because of the nanoscience and nanotechnology allowing us to actually make these elements sub-wavelengths. And as a result, you can actually do a lot of interesting things with the structure. Now, in the past 20-some years, many research groups worldwide, I mean, they have looked at, you know, concept of metamaterial. Here is there's some examples of different research groups that they make metamaterials. And of course, this list is not exhaustive. I can show you pages and pages of many different metamaterials made by many groups worldwide. Now, in my group, we are interested in various, the research programs, and these are the titles of some of the research programs that's currently going on in my group. But in the interest of time, I'm going to pick 2 topics of this, and then we'll discuss that. But I'd be more than happy to talk to anyone interested in other topics that you see over here that's currently ongoing in my group. The first topic I want to talk about is that how we can actually use the concept of metamaterial, or in general, I call it metastructures, as you will see why I call it metastructures, such that you can actually do information processing with this structure as the way it goes through them. Now, you notice I put the adjective non-periodic over here. And the reason I put non-periodic, because as you will see, if we have a structure that is non-periodic, you have more degrees of freedom. And as a result, you can do more interesting things, you know, particularly with regard to the information processing. Now, why are we interested in this? As you will see soon in the slides that I'm going to show, is that we have a longer term goal. And the longer term goal is it possible to use metamaterial for artificial intelligence, for machine learning, for neural network and so on, and take advantage of light, and particularly how fast the light propagates in material, and try to see whether we can speed up some of these processing related to the neural network and machine learning. But this is a long-term goal. In order to actually get there, we looking at the first goal we have, and the first goal we have is the following. Imagine that you would like to design a structure made of elements, let's say, as you will see on the screen, and these elements with the proper shape, proper material that you choose for these elements, and proper locations, such that this slab or this structure would have specific transfer function for the waves that you like to have. Now, what do I mean by that? What I mean is that if you actually illuminate an arbitrary electromagnetic wave, this structure, and you look at the output waves that's coming out, you would like the relationship between this arbitrary input and the output to be the transfer function you like to have. Now, the oldest and simplest of the structure that would do the transfer function for us is the convex lens. As you all know, convex lens, when you illuminate light to it, can do Fourier transforming for us. But we ask ourselves this question, why should we stick with the Fourier transform only? Why not we make our own lens that would do the transfer function you like to have? For example, to make a Hankel transform, Mellon transform, and so on and so forth. So with that goal in mind, about 6-7 years ago, we proposed this idea that is it possible to actually design a metamaterial structure? Let's say in this picture that I'm showing is a layered structure with the proper thickness of each layer and proper permittivity in each layer, such that this structure would do the mathematical operation that you like to have. For example, imagine that you have this structure such that you send a monochromatic wave with the arbitrary profile coming in, And as the wave going through this structure, by the time the wave comes out, obviously it's still monochromatic because it's a linear medium, but the profile of the output would be, for example, the derivative of the profile of the input, for example, or proportional to the derivative. Can we do this? Can we actually make a metamaterial that would do differentiation for us, or integration for us, or convolution for us? Now, indeed, we showed back in 6-7 years ago that this is possible, and we had several recipe and prescription for this in this theoretical paper we published back in 2014. And one of the application we had in mind at that time is that, is it possible to actually design a layered structure, let's say, as you see over here, with a thickness of about 1 wavelength, and the lateral dimension that could be as wide as you want, such that this structure would do second differentiation for you. Now, why second differentiation was of interest to us? Because in the image processing, you know that the operator Laplacian can give you the edges of the image. So we wanted to see whether we can actually design a metamaterial that would be edge detector, if you will. So as you send, let's say, the profile, you know, of this skyline of a city into this, by the time the wave comes out, you actually pick the edges of that structure. So it would be very interesting, you know, edge detector or for image processing. Now, current computers that you have also would do edge detection, but the way they do edge detection is by digital processing, and they have to digitize the system and then go raster scanning the entire image, and then pixel by pixel, they compare the intensity, and that would give you the derivative of that. Whereas our idea that we propose over here would be completely analog and would be completely simultaneous. In other words, the entire image would go through this at the same time rather than scanning. And that actually can save tremendous amount of time in this structure. With this theoretical proposal, then several experimental groups followed this idea, and indeed they showed experimentally that it is possible to design a metasurface that can take derivative of a wave that's coming in. So we were very excited that, you know, this is indeed is possible. So then we set our goal in a more ambitious goal. Then we asked the following question: is it possible that we design a metamaterial that can solve mathematical equations? Remember, here now we're talking about solving an equation. Previously, we were saying that we would like to design a material that would actually do mathematical operation. Arbitrary input, you get an output that is a function of the input based on the function you like to have. But now we were asking, is it possible to actually design a metamaterial that solves, let's say, this integral equation? And so as a first attempt, we decided to actually look at the most challenging linear equation. That's the Fredholm integral equation of the second kind. So in this integral equation, you notice that there's a kernel over here. And the arbitrary input function, when you put in this integral, the goal is to find the solution to this integral equation. This is function g. Now, one thing I would like to point out over here, that in order to be hard on ourselves, we decided to actually look at, you know, a tough problem, and that is the problem in which the kernel is not translationally invariant. In other words, the argument is not y minus y prime, but it is y and y prime. So obviously the convolution cannot be used over here, and we cannot use the Fourier transform to do that because this is not a convolution, and the arbitrary limit of the integral. So how do we solve this one using material? In order to do that, we have to do two things. First, we have to design a material or structure over here that will give us this integral operator for this kernel. And second, we need to actually create a feedback system such that when you send the input I over here, as the wave goes through this kernel many times, then it will come out. What comes out would be solution to our integral equation. Now, why is that? Because one way to solve the integral equation is using Neumann series. And Neumann series essentially means iterative technique. So we ask ourselves, let the light do that iteration for us. So because the light goes with the velocity of light over here, this will be much faster processing in order to do this Neumann series there. So in order to do this, we have been working on two platforms in the past past few years. One platform which I will go talk about today is using inhomogeneous material. Symbolically, we show it over here with the proper feedback system that we have. And another one, by the way, is using collection of Mach-Zehnder interferometers. Now, my good friend David Miller from Stanford several years ago proposed an interesting idea that if you have a collection of Mach-Zehnder interferometers, you put them together with the proper connection, you can actually imitate any linear operator that you like to have over here. So we said, okay, this is interesting. We can use metamaterial to have that linear operator, or we can have a collection of Mach-Zehnder interferometer, but then we need to put this feedback system in order to solve integral equations. Now, today, I'm going to talk about the left one, and but I'd be more than happy to talk to anyone interested also about the other platform. We are working on this as well. Now, with regard to the inhomogeneous metamaterial, so this is the idea. This integral equation is given to us with a given kernel and arbitrary input. Then, using the method of inverse design, we actually design this inhomogeneous permittivity over here as a function of x and y, such that it will give us this integral operator, as you see over here. And then you bring a waveguide feedback system back to this one, create that iteration that we were talking about. And then with the directional couplers, you can bring your input, arbitrary input into this. By the way, needless to say, this continuous integration is transformed into a discrete elements over here. So we have n discretization over here, as you see there. Now, so we followed this idea, and what we showed is indeed a series of simulation and theoretical work we did on this, and indeed we showed that this is possible to do. So then we decided to do the experiment. And in the experiment, we decided to use microwave frequency just to do the proof of concept, because in microwave, the system can be large enough that we can measure the different things over here. So for this integral equation, for our experiment, we decided to use this kernel that you see on the screen. Now, this kernel does not represent any physical phenomena. We just chose this kernel mathematically just to be a general kernel. You notice this kernel is not translationally invariant. In other words, the argument is not y minus y prime. Second thing is a complex kernel, as you would see, real and imaginary part it has. Third, it's not separable kernel. In other words, you cannot write this k y y prime in terms of multiplication of two functions, one function of y, the other function of. So after doing a lot of simulation, we decided to design and build the experiment. So using the method of inverse design, we came out with this distribution of permittivity. Now you see two different colors over here. The red one is the polystyrene material, Rexolite, which is a very well-known material in microwave experiments, and with the dielectric constant of 2.53 and the loss, very, very low loss. And the yellowish region is just air. So effectively what we build is that you start with the dielectric, just like you start with the dielectric, and you make specific hole region inside this dielectric with a very specific shape that inverse design has given us. And that's what in my group we call this a Swiss cheese. It's just like having the Swiss cheese, you know, holes in them. And just to give you an idea, by the way, this dimension is about 4 times of wavelength of our experiment. Our frequency was 4.38 gigahertz. So this is about 30 centimeter by 60 centimeters over here, approximately. And then we have this waveguide system that we use both as an input waveguides and an output waveguides. We did many simulations just to see a structure is working. Indeed, you see over here how the wave comes into this and being, you know, distributed. This is very interesting. You notice this is very highly non-periodic system. There's a lot of degrees of freedom in this design that will give us this kernel. And after we were convinced that the theory and simulation works very nicely, then we built the structure. So this is a rendition of that Swiss cheese that I mentioned to you. And so you would see, and then we build it, and these are the photographs of the structure that we build in my lab. You notice, by the way, there are these 5 waveguides that I mentioned to you, and there are 10 coaxial cable connectors over here. 5 of them we use to bring the signal in as the input. The other 5 we use to get the signal out, and that would be the output. And is that output solution to our integral equation for this arbitrary input. Here are experimental results. So here, imagine that we have the input as 1, 0, 0, 0, 0. By the way, this is not a digital input. The reason we call it 1, 0, 0, 0, 0, it just means the first port is being excited by a monochromatic signal at the frequency 4.38 gigahertz and amplitude 1 and phase 0. The other 4 ports are not excited. And you see over here, there's a orange plot, which is the input. But if you look at the other plots, there are 6 curves over here, 3 pairs. The dashed one shows the real and imaginary part of a theoretical result we expect to get from this integral equation, based on that kernel and the arbitrary input that we have here. The thin curve is the pair of real and imaginary parts of the simulation result. So we did the simulation of the structure we built and the numerical simulation. And the third pair, which is a thick curve, are the real and imaginary part of experimental results that we get over here. And you notice that all the 3 red curve, which is the real part, and all the 3 blue curve, which is imaginary part, agree quite well. Then we change the input to other inputs that you see over here. And you notice that for all the inputs that we have over here, and this is all the basis function of the input, then you get the solution to an integral equation. We were very excited about this, that indeed this gadget, which we call it metamaterial machine, can actually become an analog computation tool that you can actually solve integral equation. With that excitement, we decided to expand our idea to other possibilities. For example, then we asked the following question: can we have a single meta structure, a single Swiss cheese that can solve several equations at the same time? In other words, we just have a parallel processing. We take advantage of the fact that photons are bosons. As a result, they don't interact with each other. So can we actually do more than one integral equation at the same time? And the answer is yes, we could do it. We followed the idea that we proposed, but this time, in designing this meta structure over here with the distribution of permittivity, the constraint is more, because this structure, which is a single structure, should be such that when you operate it with the frequency omega-1, you would get the kernel K1, arbitrary kernel, which I will show you in a second. And if the same structure you operated with frequency omega-2, you're going to get a completely different integral operator with a different kernel K2. So we did the experiment on this one as well. So we chose 2 arbitrary kernels, as you see in the bottom of the screen. Again, these kernels are complex, are translationally variant. In other words, you cannot write the entire kernel in terms of U minus V argument. And they're also non-separable. And so then we designed the structure, and this is the distribution of those dielectric pieces that I mentioned to you. And this is a system that we built in the lab with the feedback system in the back. So there's a waveguide back line going through here. And then we did the experiment, and indeed, experiment shows, quite a nice agreement with the theory. So if you operate this system at 4 gigahertz, this is the set of results you get for the different inputs that you put it there. Again, you see the 3 pairs and 3 pairs over here. All the real quantity and imaginary quantity agree quite well with each other for all different inputs. And the same setup, exactly the same setup, if you operate it with 5 gigahertz, you completely solve a different integral equation for different kernels that you will see there. Now, right now, we have several work in progress going on in my group that we are extending this to different directions. For example, one of our original goal is to actually do this in near infrared and visible light. We did the experiment in microwave just for proof of concept, but our long-term goal is to bring this into silicon photonics. So in collaboration with one of my colleagues in the department, Professor Firuz Aflatuni, we are bringing this into the silicon photonics domain with the wavelength of 1.5 micron. So we have designed a Swiss cheese for the silicon chip. As you see, this is one of the kernel that we designed. You notice now the length of this is 30 microns. Remember, in the microwave, that was about 60 centimeters. But here is just 30 microns, which is 20 times of the wavelength of operation in silicon photonics. And this is about, 14 micron in this direction. This is the result of numerical simulation, and this agrees with the kernel that we are looking at. This is the perspective of the numerical simulation. Now, we send the design, by the way, to the foundry to be made using nanofabrication facilities, and the chip was going to come in April of 2020, but pandemic hit and the university lockdown, so that process was delayed. But the chip has arrived now and is being tested, by the way, in the laboratory of my friend, Professor Firuz Aflatuni. And we are very eager to see the experimental result, to see how it would agree with the theoretical idea. And the early indication is that we are in the right directions. And so I'm very excited to see the full experimental result. Hopefully in the next 2-3 months, we'll complete the experiment and we'll see how that goes. Another direction we are taking with the collaboration with Professor Albert Polman in Amsterdam and Professor Andrew Alou in City University of New York, we are bringing this concept into open optics. So far, we were showing it in the waveguide system, but now we would like to do metasurface with the semi-transparent mirror and to see that this structure can solve the integral equation. Again, in fact, the structure is built in the laboratory of Albert Polman in Amolf in Amsterdam, and the experiment just finished. And indeed, the result is a very nice agreement with the theory. So we are actually writing the manuscript as we speak. The third direction we are taking this is to use this metamaterial machine with the inverse scattering problem. You know, I started my career in radar. And so inverse scattering problem in radar is a very interesting problem. So you illuminate a bunch of scatterers and you measure the data, the detectors, and from the knowledge of data, you would like to know where the scatterers are. So now, in collaboration with Professor Ahmed Hourfar in Villanova University, we're trying to use this metamaterial machine that when you input the data from the detector, we would like the output tell us what these scatterers are. And this is work in progress, and we'll see how that goes. Also, we extended this concept into incoherent signal. Everything that I said so far, by the way, is coherent. In other words, we need amplitude and phase. But this idea can be extended to incoherent system. For example, if you have a matrix that is just all real number and all intensity, if you will, can we actually design a metamaterial machine that will give us that? And indeed, that's the case. This so far is a simulation and theory. We haven't done experiment on this yet. So our vision, by the way, is that in the future, we are envisioning that these so-called, we call it switches, will be the analog computers of the future, that you would be able to print them using the rewritable or phase change materials. Remember, we used to have rewritable CDs in our laptops. So one interesting possibility we are thinking about is to use that technology in order for you to print these, switches, which is about, few tens of micron by few tens of micron, and would do, integral solving techniques, so it becomes your analog computer. And when you're done with that, you can erase them and write, another set of switches. So we are looking at some of the phase change material concept. And one of my goal is to actually have a concept of FPGA, field programmable gate array, which is a very well-known concept in electronics. Can we have that in metamaterial? So in other words, can we make this analog computer programmable? I mean, that would be really a very interesting goal to have, and we are working towards that vision. So that brings me to the end of the first topic I wanted to talk about. So for the remaining moments, I would like to talk about the completely different topics. In some sense, this is also connected to the first one, because both of these are extreme scenarios. In the first one, you saw that this extreme non-periodicity, if you will, provide us with an interesting platform to do mathematical operation and equation solving. By the way, one thing I forgot to mention is that using the MZI platform, we are able to actually also solve differential equations. So it's not just the integral equation. But again, if anybody interested in that, I'd be happy to talk to everyone offline on that platform as well. But in this second topic, I'd like to talk about another extreme. And that is the extreme of near zero index metastructure. As I mentioned, my friends Onofrio, Pino, and Maria Grazia and Rosalba, we are working on a very interesting collaborative work on using epsilon near zero in electric levitation. Here, I'm going to tell you some other aspects of near zero index, that what interesting properties this system can have. Now, but before I get to some of the interesting properties, let's actually look at some of the fundamentals. Now, we all know, by the way, that if we write time harmonic source-free Maxwell's equations, we can write it in this form with the time harmonic of e to the minus I omega t variation. Now, they always teach us that if in Maxwell's equation, the field is static, in other words, when you put omega equal to 0, you get obviously electrostatic and magnetostatic, and you get the decoupling of electric and magnetic field. But you can ask yourself these interesting questions. Is it possible to design a metamaterial or to have a material in which, while the fields are still dynamic with the frequency omega, can effectively, and I underline the word effectively, can effectively E and H be decoupled for the observer sitting outside this system? The answer to that question is yes. In fact, if you design a material in which epsilon and mu will be 0 at the frequency of operation of your field, you still get, by the way, effectively curl of H equal to 0 and curl of E equal to 0. So it appears to be that these are decoupled from each other. Now, it's a very interesting scenario because on the one hand, these two expressions tell you that the field distribution in space looks like static-like distribution. But of course, the field is not static because it's actually varying with time dynamically with the frequency of omega. So it's a very interesting combination, and we call it static dynamic optics, so to speak. And the index of refraction is near 0 in that regard. And that's what we call it near 0 index electromagnetics or low index photonics. By the way, before I go any further, I would like to point out that this index has to be dispersive. In other words, it has to be function of frequency. Because even though index is near 0 and the phase velocity could be very, very high in continuous wave scenario, but the group velocity and the energy velocity and the signal velocity have to be less than velocity of light, naturally, obviously. Obviously, the causality holds true over here, so everything is fine. So in the transient scenario, we don't have n equal to 0, but only in the steady state scenario, after the system reaches the steady state, we can have that. And you will see that in the experiment we have done. Now, so before I get into the rest of the talk, let me just give you an interesting, intuition. Imagine that you have a parallel plate waveguide made of, perfect conducting wall over here. It's a two-dimensional waveguide. And so the system is infinitely extended in the direction coming out of the screen. And imagine that you have air inside and you send the TEM mode, just a simple mode of the waveguide is propagating down this mode. Now, imagine you do the following. Imagine you come and cut this waveguide. You put half of it over here. You put the other half over there. And then you ask yourself this question. I would like to connect these two waveguides with some region here, which has an arbitrary interface. And this arbitrary surface is also PEC. So this is not open and this is closed. But what material should I put over here such that when the observer sits at the entrance and another observer sits at the output, these two observers would feel that the system are still here. In other words, these two observers would not know that this structure is in between that. Now you might say, well, I can put a cavity over here and the cavity in resonance will give you that property. Yes, but then if I change the shape of the cavity, then the observer would know that's sitting over here. The goal over here that this could be any shape you want. You can change it in any way you want, and still these two observers would not know. The answer to that question is that you have to fill this region with a material with permittivity and permeability near 0. And in that case, then the wavelength inside becomes very long. So this entire structure, even though physically has some dimension, but electromagnetically becomes 1 point. 1 point, because the wavelength becomes infinitely long over here. So as a result, the structure becomes small compared to the local wavelength, not with respect to the external wavelength. So let's see what happens. Let me show you some simulation just to give you an intuition. This is the case that you have a TEM mode is propagating and comes to this region, and this is a distribution of the magnetic field. You notice that the phase difference is 0. The phase here is the same as the phase here, and the magnetic field actually oscillating with the frequency omega, and yet it looks like a distribution in space resembles the magnetic field distribution in magnetostatic, but this is not static at all. It's actually changing with frequency omega. And the electric field of that looks like this. Now, in that case, this has become even better than original waveguide, because you can put the 2 pieces of waveguide at any point you want, and the observer here doesn't see that this has a bend. So you can do it like this, you can do it like this, you can do it like this. And even in this case, 180 degrees bent, the wave comes over here and bounces back over here without any reflection. Now, let me take you back to about 15 years ago, when we started this series of interesting inquiries to what epsilon near zero material can do. At that time, Mario Silverinho, who's now a professor at University of Lisbon, he had just got his PhD from University of Lisbon, and he started his faculty position in University of Coimbra as assistant professor. So he wrote to me, he said he would like to come to my group for his sabbatical. And I knew Mario since he was a PhD student in Lisbon. So I invited him, he came to my group. And so I asked him the following question. I said, Mario, imagine this. Imagine we have a parallel plate waveguide, as I mentioned before, here with the PEC perfect electric conductor. And this is a TEM mode coming like this. And then we have another waveguide, PEC, and the mode over here. But it said, let's assume we connect these things by an arbitrary shape section like this. So obviously, if I have a wave coming like this, I'm going to get good amount of reflection, and the little will go through. But what we ask ourselves this question, what would happen if I fill this region with permittivity near zero? Do I get some interesting, transmission? The reason we were thinking about that at that time is that when the permittivity is near zero, index would be near zero. And if index near zero would be here, the wavelength would be very long, which means the phase here would be the same as the phase here. So this should radiate here based on conservation of energy, reflection should be small. But that's one intuition. But another intuition was telling us that in this region, epsilon is near zero, so the intrinsic impedance of the wave is very high. Square root of mu over epsilon. So whereas here is just basically intrinsic impedance of the air here. So in that case, do we have a huge reflection at this huge impedance mismatch over here? So these two intuitions in our head were just opposite to each other. So we decided to solve this problem to see whether we can solve it, completely. And we got lucky because we were able to solve this problem exactly analytically. And what you see over here in this expression is the reflection coefficient of the TEM mode that's coming in this structure. And this is a two-dimensional system. In other words, whatever you see on the screen is independent of the axis coming out of the screen. And the wave coming like this. And we notice that this would be the reflection coefficient of the wave coming over here. Now, let's go over this a little bit. If I want this reflection coefficient to be zero, I have to make sure the numerator is zero. But the numerator has a real part and an imaginary part. Okay, I have to make the real part zero. But a real part means A1 should be equal to A2. Okay, that's fine. That means the two waveguides has to have the same height. That's fine. But how can I make the imaginary part zero? So imaginary part is multiplication of three quantities. If I make any of them zero, then I achieve my goal. So can I make K naught zero? But what is K naught? K naught is omega frequency divided by velocity of light c. That means I have to make frequency zero. But that's not interesting. That means if I put a battery over here, I get the same voltage here. Not interesting and obvious. Another possibility is to make mu sub r equal to zero. But what is mu sub r? Is a relative permeability of this region. Epsilon is already zero, so if I make mu zero, then I have impedance match. But at that time, 15 years ago, we didn't want to touch mu equal to zero. Now we are doing mu equal to zero, but not at that time. So we didn't touch this one either. But the third quantity was the most interesting one, A sub d. I haven't told you what A sub d is yet, but A sub d is this cross-sectional area that you see over here. Now that was very counterintuitive to Mario and me at that time, because what does this mean? That means if I make the A sub D near 0 while keeping A1 and A2 fixed, then I get less reflection coefficient and more transmission. This was very counterintuitive. What that means is if I get this throat of this waveguide and I bring the throat narrower and narrower, the wave actually tunnels through this better and better. So we said, well, this can't be the case. I mean, how is it possible? So we double check, triple check, everything we did, you know, we said this expression completely satisfies Maxwell's equation. We did a series of numerical simulation, exactly agreed. And so we published this theory paper at that time in PRL. And then 2 years later, we did the experimental aspects of this, and it completely agrees with our theory, which I will show you in a second. So this actually started an interesting movement that call it, you know, ENZ or epsilon near 0, because it effectively showed a very interesting property, which we call it supercoupling, that happens over here. By the way, one thing I forgot to mention, please note that this expression does not have any indication about this angle. So you can make this angle anything you want. Even you can make this angle 180 or 0 degrees, as you will see in our experiment. So let me give you an intuition. Imagine that you have this waveguide, you have it over here, PEC, and you have this huge abruption over here in the geometry. If you send a wave over here, you expect to have a lot of reflection. Let's see. And indeed you have. So you see these are very good, you know, we have a lot of, you know, reflection over here, so we have a complete standing wave over here. But now what we're going to do, we're going to put a material over here, just this little region, and we're going to change the permittivity of the material, and gradually we bring it down. Let's see what happens. If I put a material there and I make epsilon relative 0.5, you notice that still we get a good amount of reflection, but there's a little wave leaks through this real narrow channel. Then we make the epsilon even lower, and you see more is leaking through this. And if you make the epsilon very small, all of it will go through this. It's very interesting, by the way, you notice that this electromagnetic wave is squeezing through this narrow channel without having any reflection and shows up to the other side, kind of reminds us of, you know, like an electromagnetic version of the Bernoulli's law, that the fluid dynamic is going through the system without having the reflection there. So look at the two extreme scenario when there is no ENZ in this tiny region, epsilon 1, and when there is ENZ only in this U-shaped region. The rest is air, by the way. And you notice this wave is coming and hitting this metallic wall with a very thin layer of ENZ, and everything squeezes through this and go to the other side. So you may ask, you know, do we have any material with epsilon near 0 structure? Yes, we do. In fact, in the near IR transparent conducting oxide, several property, indium tin oxide, aluminum doped zinc oxide, gallium doped zinc oxide. This data is from my collaborator Sasha Boltaseva at Purdue University that shows that the very interesting, you know, 0 crossing at 1.2 micron. And then the imaginary parts is about 0.1, and actually that's relatively high. In some application we don't want that, but in some other application that's good. But silicon carbide is even better because you have a 0 crossing at 10.3 micron, which is a CO2 laser wavelength, and the imaginary part is very small, it's about 0.03. Topological insulators, some of them in the UV regime, this is the work of Nikolai Zheludev that showed that in 200 nanometer wavelength this becomes 0. But if you like to have your own ENZ material at the wavelength of your interest, then you can actually use the concept of metamaterial to make them. For example, you know, my friend Pino Stranges, you know, has done a lot in his lab, and this is an earlier work by Anatoly Zayats and Albert Polman, showing that the layered structures, you know, can provide this one there, and Pino has done it with a very different set of systems. Or if you're working in microwave domain, you can get, you know, just an empty waveguide and operate it at the cutoff frequency. And in that sense, you imitate, you know, the property of ENZ structures. And in the visible domain, by the way, C.T. Chen from Hong Kong University of Science and Technology has shown that you can actually create a photonic crystal with the Dirac dispersion with accidental degeneracy that can give you the effective n and effective epsilon near 0. Now, back in 2008, we did the experiment with microwave, and indeed we showed that you can actually have this very interesting property, which we call it supercoupling in E and Z. You notice in this microwave, this region over here, this U-shaped region, is the waveguide at cutoff, and the wave actually tunnels through this one. And when you change the L, you still get, by the way, supercoupling at the wavelength of E and Z without changing. You make it 90 degrees, you make it 180 degrees, still the system works. So effectively, you have a waveguide system that behaves like a wire in your room. If you have a wire in your room and you bend it, you're not going to have reflection in electrons there. Here, you make that for electromagnetic and optical wave that you can actually bend them. By the way, Onofrio and Antonella, how much time do I have? I don't want to impose time on the audience.
Don't worry, it's okay. I mean, you have some time left.
Okay, please let me know, by the way, if I'd be happy to stop anytime. Thank you, Onofrio. So we, after these works, then we were very excited about these properties of E and Z. So we decided to look at the various different aspects of these. So one of the aspects was this one: can we actually use this type of structure for enhancement of optical dipoles for fluorescent molecules? And the reason we were thinking about that is because I showed you this picture before, that you see the wave is tunneling through this very narrow channel with no reflection. And you notice, by the way, the phase difference is 0 over here, indication that index is near 0. But you notice that the electric field is very strong over here compared to this. And that, of course, it's understandable because the wave has to squeeze through, so the pointing vector here is stronger than this. So we said, because the electric field is very strong, could we use reciprocity? What would happen if I put an antenna over here? If I put an antenna over here, even though this is a very narrow channel, antenna should radiate very well. So together with Andrea Liu and Stefano Marchi from Italy, we actually look at, the microwave theory of this, and indeed that supported our intuition. But my goal was to actually extend this into visible domain. But the question was, how can I actually put an optical dipole or fluorescent molecule at this point? And that would be very hard to put that. So one time I was giving a theory talk in a conference, and in the coffee break, my friend Albert Polman from Amsterdam came to me and said, I have an equipment in my lab that can actually do what you like to do. So, and that was the cathodoluminescence spectroscopy that Albert had. So we joined forces with Albert. I went to his lab for 1 week in Amsterdam, and we designed actually a microwave, we designed a waveguide, but this time for the visible light. So this is very similar to that microwave waveguide that we built in my lab, but now this is actually an optical waveguide. It's about just only 2 micron. And this is about 85 nanometer that we built in Albert's lab. And this is the cathodoluminescence spectroscopy electron beam come over here, hitting the sample, and at that point give rise to emitted photons. And so as a result, essentially, it's just like putting an optical antenna at any place you want with the resolution of about 4 nanometers, point by point. You can do that. So this is the comparison. This is actually the experimental result that we got from Albert's lab. This is the electron beam is coming normally to this waveguide. Imagine the electron beam is coming normally to the screen. And at every point the electron beam hits, we look at the location of the electron beam versus the emitted photons wavelength. And you notice that when we have a waveguide with the width of 180 nanometer, this waveguide becomes at cutoff. So indeed, experimentally, this was shown in Albert's lab with our collaboration, that indeed this becomes the E and Z structure at that point. Albert and I later on actually extend that to some of the other materials in his lab and show that indeed this becomes, epsilon near 0 structure. Now, with our friends, Pino Strangi and Onofrio Marago and Maria Grazia and Rosalba, we actually are looking at the electric E and Z levitation. And the idea is the analogy with superconductivity. So the idea is that in superconductor, we know that the Meissner effect can basically levitate this magnet. So can we actually have a dual of that in epsilon near zero material? Could we actually have some structure that would repel the vector D instead of vector B? So this dynamic dipole can be levitated. The theory work that we did back in 2014 indeed proposed that this would be a possibility, but now together with Onofrio and Pino and members of our group in this collaboration, we are trying to see how this actually can be done experimentally. And I want to thank Onofrio and Pino and all the collaborators for the great effort they're doing on this. We are very excited about this, and we'll continue our collaboration to see how this thing can be shown experimentally. You can actually have other features. For example, you can have ENZ transistor. By changing the permittivity over here, you can have, like a source and drain, changing this, significantly. There is some interesting nonlinearity properties of that, which we showed in the microwave domain using the varactor. So this varactor can actually be self-tuning itself depending on the power of the microwave, because there's a very high electric field happening there. Recently, several groups, Bob Boyd's group and Vlad Shalayev, Sasha Boltaseva, and Daniele Facio's group, and also Luca Dal Negro with our collaboration, showed that nonlinearity actually could be quite strong in the near infrared for ITO as well. So this is actually another interesting direction for ENZ going on. And so one last item I want to talk about is what interesting cavity structure this thing would have. We all know, by the way, that when you have a cavity, the resonant frequency, of course, depends on the shape. If you change the shape of the cavity, the resonant frequency will change. But what would happen if you have a cavity made of epsilon near zero structure? Indeed, we showed that such cavity has a very interesting property. In this theory work that you see over here, you see that we study a cavity made of ENZ, and this is open cavity with a dielectric core. And this is the distribution of the electric field of the mode, and this is the distribution of the magnetic field of that mode. You notice this is a very interesting mode. This is a mode that's confined within an open cavity. So it's effectively just like a bound state in the continuum for photonics with the arbitrary shape of the external shape. And you notice in this shell, electric field is non-zero, whereas the magnetic field is zero, and yet the field is dynamic. And this is the decoupling of electric and magnetic field I was referring to at the beginning of my talk on this section. We call it flexible open cavity. You can change the external shape of the cavity, any shape you want. The resonant frequency of that cavity does not change, but the Q and quality factor of that changes. And this actually becomes a very interesting platform for quantum optics, because people in quantum optics, they would like to couple an excited atom to a cavity, but the transition frequency and the resonance of the cavity should match perfectly. If you change the cavity, then the cavity would be detuned, but not here. If you change the shape of the cavity, cavity would not be detuned. Cavity would stay at the resonant frequency, but then the Q can be controlled. We experimentally verified this, in my lab using microwave. We built 3 different cavities, arbitrary shape, as you see, but the same cross-sectional area, and we put a dielectric dopant over here. This is one dielectric dopant, not 3, but we put it at 3 different locations. And then, according to our theory, the resonant frequency of these 9 different scenarios, 3 different cavity with 3 different locations of this should be the same. We built it, we tested it, and indeed, all the resonances happen at the same frequency experimentally. This can have a very interesting effect in quantum optics. We are working to look at, how this can affect the vacuum fluctuations, quantum vacuum fluctuations. Indeed, our theory work showed that this structure, you can create a structure that inside of this is the void of any electromagnetic mode. So essentially, you can bring or harness the vacuum fluctuation to very small values. So if you put an excited atom over here, that excited atom would not decay, or would decay at a very slow rate. And finally, this is my basically last 2 slides. Very recently, in fact, the paper came out September 2020. One of my former postdoc, Inigo Liberal, who is now a faculty in the Public University of Navarra in Spain, he came out with a very interesting observation that there is interesting analogy between epsilon between near zero index electromagnetic media, and ideal fluid. In fact, there's a very interesting connection between what an ideal fluid would do and what the optical power flow would do in ENZ. If you get a structure that is epsilon mu near zero and you send a wave through this, you notice that the wave goes very smoothly without having any optical vortex. But if you have a regular dielectric, you're going to have a lot of optical vortices over here. This becomes very interesting analogy between fluid dynamic and ideal fluid and near zero index structures. That brings me to my last slide and the summary slide. I would like to thank again my friends Onofrio and Antonella and all the friends in the University of Messina for the kind invitation and giving me a chance to talk to you about these two topics that's going on in my group. Thank you so much. I'd be happy to answer any question.
Thank you, Nader, for this great talk, this great view over this amazing research field. So I think we can now open the session for questions. So I'm not sure how, Dino, can you help me with this?
About what, Onofrio? Sorry. So I think
someone wants to. Okay, so anyone can ask questions.
Yeah, okay. People can raise their hand here on Teams, or they can simply speak. I think.
Okay, perfect. So any question? Okay, so I'll start.
Yeah, sure.
Okay, there is one. I think that
there are two people. Okay.
So yeah, you either Onofrio, you can read the question or I can read the question, whatever is easier for you.
Okay.
Oh, okay, so maybe people can just talk. I mean, they can.
Yeah, exactly. I mean, you can go. By the way, my apologies that I went over time. I'm sorry about that.
No problem.
Oh, it is okay.
There are two questions. I think Fabio Mauceri.
Fabio Mauceri. Okay.
I think your microphone is muted. And I can see my friend Andrea Cordaro there. So Andrea, good to see you.
Can you hear me now?
Yes.
Yes.
Please go ahead.
Yes, I have a question about the quality factor.
Okay.
The tunable quality factor. That depends only on the shapes of the cavity, of the external shape, or it's more complicated.
Yes, very good point. Fabio, I assume you're referring to the ENZ-based cavities that I was talking about. Yes, that's right. Very good question. Yes. So that cavity, which we have some, regular dielectric dopant, we call it dielectric dopant inside of this. The resonant frequency of that cavity is actually ENZ frequency. So that's very, straightforward for that. So as a result, when you change the external shape of the cavity, you change the field distribution inside the ENZ region. But you don't change the resonant frequency, or you change it very, very slightly because of the presence of loss. So because you're changing the field distribution inside the ENZ region, and your ENZ has some loss, in that case, the quality factor can change. So it's interesting. In other words, this is a very unusual cavity. In a regular cavity that we all work with, when you change the cavity shape, resonant frequency would change, and of course, quality factor will change. So quality factor is coupled with the resonant frequency. Here, that's not the case. When you change the actually external shape or the location of the dielectric dopant, you can also change that one as well. You do change the electric field distribution. You do change the quality factor, but not the resonant frequency.
Okay.
Yes.
Okay. And you can actually choose what quality factor you are going to wave, or at this point is not so.
It depends on several parameters. It depends, of course, on the shape, as we talked about, but also it depends on the loss of the ENZ. And that's important. So it depends on the loss of ENZ. And for example, if I can share my screen again, I can show you, by the way, those quality factors that we found. Let me see. Oh, here. Okay. Let me go back. Let me actually put this in the. Let me go back to that cavity here. Fabio, this one. So this is we have a dielectric rod, which is silicon over here. This is theory work, by the way. This is entirely simulation. And then you have very different shape. And by the way, these shapes are not discrete shapes. You can actually merge them from this to this, from this to this. So you can have any shape in the external shape. And this is from our simulation using the parameter of silicon carbide, which has the imaginary part of 0.03. You notice that the resonant frequency is almost the same over here, as you see. But the quality factor, which is this factor that you see on the right, is changing significantly, depending on the shape of this that you have there. So, and then you notice, by the way, in this case, quality factor is around, a few hundreds that you have there for that material that we use in our simulation. Yeah. Now, in the experiment that we did in the microwave, it's also there, but here you don't see it. I can send you the paper and we have the expression. So you notice over here that all the resonant frequency happen at the same frequency, but you notice that the height of this transmission coefficient is different. That's just because you have different quality factor. So in these different, cavities that we build, with the 3 different location of the dielectric rod that we put there, you get different quality factor. And from this experimental result, you can actually see how quality factor is changing over there. Of course, this is in microwave, is for that cavity.
Okay, thank you very much.
Sure.
Okay, and next question from Andrea. I don't know.
Hey, hi, I'm Andrea Cordaro. Thanks, Nader, for the great talk.
A collaborator, so we know each other very well. So
yeah.
And he has done a great job, by the way, with that meta surface structure.
Thanks.
Okay.
So I have actually a small question about the ENZ supercoupling between the waveguides.
Sure.
So I saw that there's also a little bit of ENZ material actually outside the coupling piece.
Yeah.
And I was wondering, why is that? Like, is that something that has to do with like numerical stuff, or it's really?
No, that's actually quite a very interesting point. So again, let me share that, if I may. Let me bring it to, let me first bring it to this page. Now, Andrea, the original idea when we were working in 2006, almost 15 years ago, is that we wanted to make sure that this TEM mode that's coming over here, when it hits this boundary, would hit that boundary normally, because that's the only way that can tunnel through this. Okay, so that we started with that. Then when we went to this is the general shape that we were proposing at that time. But when we went to the shape like this, for example, then you notice that, yes, I put a little bit of these things over here. Now, it's very interesting because when you put this one over here, this sharp corner that you see over here, that sharp corner is giving you a very interesting capacitance. And if that sharp corner is entirely immersed in the ENZ, that effect of sharp corner is different than if you bring this ENZ at this point. If you bring at this point, that sharp corner, part of it would be in air, part of it would be ENZ. Now, supercoupling will still happen, by the way. The effect will still there. However, there would be a slight change in the shift of the frequency. So what's happening essentially is that if you bring this ENZ and you stop it over here, then you have a combination of C, and then that C has to be compensated by an equivalent inductance. So that's why, as a result, the frequency of supercoupling will be shifted a little bit to the red, because then the ENZ is slightly become negative epsilon. And you do that, it will work. So yes, in fact, Andrea, Lou and I addressed this issue in one of our theory paper, I think it was 2008, 2009, which I'd be happy to send you to see some of this. Yes, this doesn't stop the effect if you don't put it over here. The thing is that if you actually keep it over here, the supercoupling frequency happens to be very close to ENZ frequency. But if you bring that one out, then slightly will be shifted. Yeah.
Okay. Okay.
Actually,
Thanks.
there's another interesting explanation there. If you plot the pointing vector of this, I didn't plot the pointing vector here, but you can plot the pointing vector. You see what happens. Pointing vector gets to this very tiny region of ENZ, bends around and go through that channel. So if you don't have that ENZ there, pointing vector still bends around, but it bends around before it gets to the metallic thing. It bends around in air and goes through this. But the effect will be there, but slightly shifted in frequency.
Okay. Thank you.
Sure.
Okay, thank you. Further questions, please? Let me check. Okay, regarding, once more, regarding losses, I was wondering, because when you squeeze the electromagnetic field in such a small space, I guess you have an increase in energy. And so if you have some dissipation, this could basically become the limitation of the device, if you see what I mean. So I was wondering,
Sure.
how important is this dissipation, and I guess this will give also a figure on the kind of structures that you can build in practice.
Excellent question also, Onofrio. Thank you for asking that. Let me address that point in two steps. One is the loss of the wall of the material. The other one, loss of the material of the ENZ. So let's split that into two parts.
Mm-hmm.
The loss of the wall. Now, this is actually quite interesting. You might think that, okay, if I have this wave coming like this, of course, in this one, we assume is a perfect conductor. In our experiment, we had aluminum, which is relatively good conductor in microwave frequency. But we have also done a study on the optical frequency when you use silver. In that case, of course, the wall is lossy. It turns out, by the way, and this is one of the peculiar features of this ENZ supercoupling, is that even though electric field is very strong over here compared to the electric field here, magnetic field is the same. Mm-hmm. So this is interesting. In other words, in this structure, magnetic field in this ENZ region is the same as the magnetic field outside. Now, what is the implication of that? Implication of that, it means that the loss, that the current in the wall is the same as the current in this squeeze region as well as in the other region. So by bringing the walls closer and make this throat of the waveguide narrower, you're not changing the current in the wall. So the loss of the current in the wall is the same. Okay, so that's a good sign. Now, but there's another mechanism for loss, and that is the loss of the material. Mm-hmm. That's interesting. And it's a very interesting point. Remember that when we bring this height down, the electric field would increase because the pointing vector should stay, the integration of pointing vector should stay the same. Because you're bringing the height down, electric field would increase by that factor, but the reciprocal of that. So that means E squared would increase, and that means multiply by the loss of the material. But also bear in mind that the volume has decreased. So it's an interesting thing there. And yes, if you squeeze that, then loss, indeed, it would affect that. There's no question about it. But it works not as bad as one would think. I mean, it's not like it's the same, because you increase the electric field by a factor of 1 over height, but you decrease the volume also by a factor of 1 over L. And so when you multiply this together, I'm sorry, by a factor of L, so you end up with the loss being 1 over that length. So when the length is decreasing, yes, the loss would increase. But it's not like a L cubed. You know what I'm saying? It's not like that. It's weaker than that. And in fact, one interesting point, because of that, the signal that you get over here, in fact, let me show you the experimental result. You will see that very nicely. You notice, so let me put it here. This is interesting. So in this plot is the magnitude and phase of the transmission coefficient of this structure. Now you notice, by the way, that what are these? The blue curve is a simulation curve, and the red curve is experimental curve.
Mm-hmm.
You notice the simulation would tell us that the transmission should be near 1, but
Mm-hmm.
experiment was not near 1, was about 0.6, and this is the transmission coefficient. Now, at first we were very puzzled that why the transmission is not close to 1, because if it's because the aluminum is not that lossy. I mean, in microwave frequency. It turned out, by the way, that it wasn't because of aluminum. It turned out that in the experiment we did, you notice that we put this piece of aluminum on top of an optical table. In fact, you see it over here. But in order to make sure that there's electrical contact between the metal and optical table, we actually put a conducting grease between the aluminum and optical table. Now, conducting grease is a good conductor, but for DC. In microwave, it's very lossy. So this effect of the loss was because of the conducting grease that we put on the wall. So we redid this experiment later on by making a complete one piece of brass, and we made the things there. And in that case, the transmission coefficient came to about 98%. So and this is because of the wall. Now, if you put a lossy material inside of this, then you're right. Then we will have loss, but not as bad as bringing the volume complete. In other words, the loss here is better than the standard plasmonic loss.
Okay.
Yeah.
Okay, thank you. Any other question?
I have a question, if possible.
Sure.
Yes, please, Pino.
Yeah, Nader, thank you very much for your talk, as usual. You are very inspiring. And so my question is a question to a visionary scientist, right? So you're a visionary scientist, and I'm asking what we should envision, as a scientist in this field, as next step that will be a breakthrough, that will change the world in a way that we would like to see. You talked in your last 5-10 years of many great, beautiful ideas, Metatronics, now metamaterial machines, systems to materials that make mathematical operations, and so on and so forth. But can you show us in a minute, maybe, what is your final goal? What is your, the vision, so that we can follow, maybe we can help somehow, if we can.
But Pino, thank you so much. You're my dear friend and brother, and you're very kind to me. I don't know whether I am that visionary to answer your question, but let me try at least.
Okay.
Let me try. I think one, in my opinion, my humble opinion, I think one possible directions is that we see already, by the way, in the community, and that is, can we use material in order to do computation, particularly, and this is one of the things that we would like to do as a next step, particularly to do nonlinearity. I mean, as you know, nonlinearity is one of the heart of the computation. And in fact, if you look at digital computers and so on, transistor is a natural, nonlinear, quote unquote natural. Obviously, we build transistor. The problem is in optics, nonlinearity is always very weak. So can we actually have some form of material that would have hugely enhanced nonlinearity? I mean, that would completely, change the paradigm, if you think. If you look at a lot of interesting biological system, and I know you love biology and you're one of the pioneers, in the area of biological aspect. There's a lot of nonlinearity in biological system. I mean, look at the way our brain works. Look at the way, in fact, I always tell my student this simple example of auditory system that we have. Our auditory system, you can hear a mosquito and you can hear a cannon firing. That fantastic range is because you have a gain control, in our system. So that nonlinearity is huge. Can you imagine if we can make a material that has that huge nonlinearity? It's a game changer. I mean, if we can do that, it's absolutely game changer. Now, Microwave people already have done a lot of nonlinearity, but nonlinearity in microwave is rather available. I mean, you buy a few dollars varactors and you can have a huge nonlinearity. Diode is a huge nonlinearity, but in optics, I mean, that's a challenging one. So if we can actually have nonlinearity so huge in optics, that's the game changer in the material. So that's one possible direction. And you can imagine if we can do that, a lot of interesting biological system can be built, you know, on the optical platform. And that, of course, relates to neural network. After all, neural network is based on nonlinearity. So that's one direction. Another direction, it may sound crazy, but can we actually have optical materials that heal themselves? I mean, this is something that, you know, I've been thinking about. I mean, why is it that in biology we have systems that heal themselves? I mean, if we have a cut in our hand, after a while, I mean, the cells will get back together and that cut is healed. Can we do that in material with light? Now, people have looked at, by the way, I mean, systems that are can change it, like a phase change material. In a sense, is that, you know, one direction about that. But would it be possible to actually have, let's say, imagine that you have a waveguide system, that there is a cut in the middle of the waveguide, but the light that's going through that heal itself. Now, that would be fantastic. And that happens in our body. I mean, when we have a cut and we heal it itself, can we do that? And and also, by the way, the areas that becoming very hot topic for many fields, like machine learning and so on and so forth. I have a colleague at Caltech, Yasser Abu Mustafa, who wrote a book recently called Learning from the Data. I mean, his area is signal processing, learning from the data. Can you imagine that, you know, if we can use a material, and that's one of the reasons we are, moving towards this, you know, metamaterial machines and so on. Can we use a material that would do computation for us much faster, in much higher, capacity, and we try to learn from it. I mean, if you think about it, learning from things. After all, if you look at the history of science, you know, if you go back to the 19th century, how did Michael Faraday actually came out with the Faraday's law? It was observations. It was just observation. I mean, in a sense, he learned from the data. Learning from, and the entire physics of, foundation of physics is based on learning from the data. And Galileo did that, you know, Faraday did that, Newton did that. These are all based on the data that you say, okay, what is that law? Now, can we do that much faster with much higher things? And I think, by the way, the future material plus machine learning plus neural network, it is in that direction. So, I mean, so these are some thoughts.
This is great. Thank you very much, Nader. Because you know, I usually enjoy having, you know, this conversation with you, and you know, I wanted to see how if, you know, this means something has changed in your mind. But I see that you're a river, you know, full of ideas.
Thank you.
So, but I noticed something. I want just to make a comment on what you said. I noticed that you mentioned more than once, you know, life, biology, and how life, you know, can enter in biology, and, you know, life sciences can enter in the design of a new material. I think that mimicking nature and taking ideas from nature and what nature has done in the long haul is something that, you know, we should learn more and take more into consideration for the future when we design materials. And when we ask, you know, to our machine learning system to be unsupervised or supervised, we should ask nature to supervise it. Absolutely right. Absolutely, I agree. But may I add something to that vision if we have time? I mean, I'd be happy to talk to you now offline. We can do it. Yes, I mean, we can learn a lot from nature. That's very true. But two things we should consider. This is, again, my personal opinion, is that nature had a lot of time on its hand to get to this point, billions of years and so on. And that's why, you know, because of all the possibilities, you know, it comes to this point. That's one issue. The other issue is that there's a lot of elements there.
I mean, the law of large numbers, so to speak, or the phenomenon of emergence. When there's a lot of things get together, the emergence happen, and you're very familiar with that concept. So that's actually a very good point you're raising. So can we actually do that in optics, in material? Because optics can move with the velocity of light. So if you want to have a lot of iterations, can happen a lot of iterations, by the way, in much faster time. In fact, that was one of my motivation to come up with metamaterial machine. In other words, rather than the Neumann series that's done by the computer electronically, I mean, you go repeat iterations, let that be done by light, because the fastest things in universe that can do that. Now, can we actually do that, for example, in this process of biological process? You know, biology had, billions of years to try many different things to get to where we are. Can we actually accelerate that in a sense, using other phenomena in nature, like light? Imagine, for example, if you want to have 1,000 cycles, if that 1,000 cycles happens to be 1,000 years or 1,000 milliseconds, that would happen through light. But also there's another thing, by the way, and this is something that, in my own experience, as you know, that I have another line of research activities in biological visual system of imaging system and so on, that we were inspired by eyes of animal species. It turns out, by the way, if you look at some of those animal species and the way their eyes evolve, which has a fascinating possibility, but they're not necessarily optimal. See, this is one thing, by the way. Nature is not necessarily optimal. It's working, but not necessarily optimal. But can we also add our own intuition to that and make it optimal? For example, when we look at the eyes of fly or insect, okay, they have 15,000 this unit called ommatidia, which is a very low resolution, by the way, but they do something else. They can actually detect emotion, for example, better than human eye can do, or they can see polarization that our eyes cannot see, for example. But when we wanted to build a camera system kind of inspired by that, we didn't need to stick with the 15,000. We went to 1,000,000 pixels, let's say. So that's something that the nature hasn't done there. Nature has done it, 100 or 200 millions in human eye, but we don't have a polarization capability. Those species have 15,000 instead of millions, but have polarization capability. But why not actually have both? Because now that we have a technology, we can do that. So yes, we can actually learn a lot from nature. I think that should be a guideline, but also we can add our own parts to it, because nature is not necessarily optimal. It has done based on evolution, something on top of something else. So it's one win through this. And again, I'm not a biologist, so I don't know anything about that. But based on this, so we said, very good, let's just learn from both of these and try to see that. And I think light is a fascinating thing, by the way, and material is a fascinating thing. And combination of these, I think we can do a lot of things in the future.
Thanks. Many thanks.
Thank you. Thank you for the.
Thank you. Thank you, both of you. And any more questions? Okay, if not, I would like to thank Nader again for the great talk, for this great opportunity to have you with us. And I don't know, maybe Dino wants to say something and to close the session. Thank you again.
Thank you very much, Onofrio, Antonella, Dino, Alba, Mario Grazia, all of you. Thanks very much for this opportunity, and I look forward to seeing you in person. I mean, here in Philadelphia or in Messina or Calabria, anywhere that we get together. That's the important thing, is the friends be together, no matter where in the world.
Indeed.
Thank you, Nader, also from my side and on behalf of all the group of Appunti di Fisica for this nice talk. And of course, I hope to see you in person. Maybe Messina, because this means in any case that all this very tough period of emergency will be more or less solved.
Yes.
Okay, so I hope to see you again in person.
Thank you, Dino.
Okay,
I'm very much looking forward to seeing you, and we all hope that this pandemic will be over and we all get together in any place that we can have a good time. Discuss scientific topics and enjoy our friendship together. Thank you.
Yes, so thank you again. Thank you to all people who followed the seminar of Nader Engheta. And so I will stop the record. And as I said, so I start to record a few minutes over. I mean, after Onofrio start to talk. So your talk is safe, but the presentation of Onofrio is a little bit, it has to be shortened because I forget, as I said, I forgot to start the recording. Okay. Okay, so see you.
Wonderful.
See you
Thank
at
you.
the next seminar. Okay, bye-bye.
Thanks.
Bye-bye,
Bye.
everyone.
Thank you, Nader. Bye.
Bye-bye.
Bye.
Bye.
Bye-bye.
Bye.
Yes.
See you soon.
Bye.
Bye.
Ciao.
See you soon.
Ciao.
Bye-bye.
Ciao. Ciao, ciao.
Ciao a tutti, ciao Dino, ciao Onofrio, chiudo anch'io.
Grazie.
Ciao Giuseppe, ciao.
Ciao.